Good evening, everyone, and welcome to today's live session for the course Introductory course in Real Analysis. So, this is the 10th session in this course. So, to begin with today's session, we'll first look at this problem which was left unsolved in the last session. So, we'll try to see it today and try to solve this. So, let's look at the very first statement. So in these questions you have to check whether the following statements are true or false. Okay, so to begin with, let's look at the very first line. So it says that composition of two uniformly continuous function is uniformly continuous. Okay, so to this question, in fact it's true, and to prove this you can proceed in the following way. Okay, so what you have been given is, so we'll assume that we have been given two functions. Okay, so suppose that f from x to y, and okay, so this, okay, and g, let's say from y to z. Okay, so assume that they are given two functions which are uniformly continuous. So f and g are uniformly continuous. Okay, and our claim is, so what we'll show, so claim is that g composed f, okay, this will be a function from x to z. Okay, so the claim is that this is uniformly continuous. Okay, so this is what this is statement, when I say that this statement is true, this is what it means, that if we choose any two uniformly continuous function such that their composition is meaningful. Okay, so that's why here I have chosen the codomain of f and g of domain of g to be y. Okay, so and then we say that g composed f, which is a meaningful function from x to z, is uniformly continuous. Okay, so this statement is true, and we'll try to see the proof now. Okay, okay, so what is the meaning of uniformly continuous? So uniformly continuous basically means that, so let me write it here. What do we mean by uniformly continuous? So it basically means that if I choose any 2 points from the domain x, okay, so for, let's say that for given epsilon greater than 0, there exists a delta greater than 0. So, and the main thing is that, okay, so delta greater than 0, it is independent of epsilon. So there will exist a delta such that if I choose 2 points from this x which are close enough, which are delta close enough, let's say, then my functional value will be epsilon close. So there exists delta such that for, okay, so such that for x, y in x, or let's say x1, x2, with mod x1 minus x2 less than delta, implies that f of, or g composed f, let's say, so let me say this is h, so maybe let us write this as h, such that h of x minus h of x1 minus h of x2 is less than epsilon. Okay, so if I choose 2 points from the domain which are close enough, then my functional value has to be close as per my desire, right? Because this epsilon is something that I can choose. So this closeness is according to me, like whatever, how much close I want, I can make it, given that my points x1 and x2 are sufficiently close. Okay, so this is what this, the main thing is, that what is different from continuity is that over here it's true for all xy, for all pairs x1 and x2. Okay, and this delta, so in case when we talk about continuity, this delta is something which depends on the point of continuity. So when I say, let's say that f is continuous at c, then this delta will depend on that point c and on the choice of epsilon. Okay, so depending on epsilon, I will get a delta such that fx minus fc will be less than epsilon if x minus c is less than delta. The main difference is that this delta is independent of epsilon over here. Okay, I hope this is fine. So now we'll try to prove this claim. Okay, so what we have been given, let's write what we have been given. Okay, so anyway we have to prove that this composition is uniformly continuous. So we'll first choose some epsilon, right? So let epsilon greater than 0 be any arbitrary number, right? Then we have been given that f and g are uniformly continuous. So there exists, so the first thing is there exists some point positive number delta 0 such that this, let's say, g of y1 minus g of y2 is less than epsilon if, I mean, this y1 y2 are close less than delta 0, and f is uniformly continuous. So there exists delta 1 greater than 0 such that f of x1 minus f of x2 is less than epsilon if x1 minus x2 is less than delta 1, right? So we'll get existence of such delta 0 and delta 1 due to uniform continuity. Okay, now what we have to prove, like we have to prove something like this. Okay, so we'll start with that. So now let us look at this g composed f. So g composed f at x1 minus g composed f at x2. Okay, what is this? This is nothing but g of fx1 minus g of fx2, correct? Okay, so now what we can do is, so let me write it in this way maybe. So I'll choose x1 x2 close. Okay, so let me start from here. Okay, so see what I want now. I want this over here, I want to use the some uniform continuity of g, right? This is what I want to use. So now I'll choose, so these x1 x2 are same as this one. Okay, so I'll write maybe, meaning that this x1 x2 satisfies this property. Okay, so let x1 x2 belong to this given capital X such that this mod of x1 minus x2 is less than delta 1. Okay, now the moment I have chosen this, okay, what I can say is, so this epsilon I can choose whatever I want, right? So let me say here that I will choose this epsilon over here to be equal to delta 0. Okay, so maybe I should write here properly. So let me write here that since G is uniformly continuous, since G is uniformly continuous, there exists delta 0. And now, so here this is corresponding to this epsilon. Here what I will write is that for delta 0, since f is uniformly continuous, okay, since f is uniformly continuous, so for delta 0, okay, for delta 0 greater than 0, there exists delta 1 such that this thing happen, right? So now I am choosing x1 which satisfies this one. So that would mean, this would mean that f of x1 minus f of x2 is less than delta 0, right? Now this would mean from this one, so maybe let's say this is 2 and this is 1. Okay, so this is by 2. And now since fx1 and fx2 are close, delta 0 close, and these are in y, right? So this belong to capital Y, this belong to capital Y. So now I can use 1, okay, to conclude. So this would imply that g of f of x1 minus g of f of x2, this is less than epsilon, and this is by 1, right? And this is nothing but this composition. So maybe I can delete this one, maybe delete and then put it here, this. So this is nothing but g composed f x1 and minus g composed f x2, and this is what we were supposed to prove, correct? So we have chosen epsilon as an arbitrary number, and this delta what we are getting here is the same delta what we can get for using the uniform continuity of f. So this, with this delta 1, I am getting this relation that g composed f x1 minus g composed f x2 is less than epsilon. Okay, so this is quite standard stuff that you can do. Okay, so now I hope this is clear to you. Is it?
Sir,
yeah.
whether you have to choose the same epsilon for the functions f and g?
No, I have chosen different. So see, initially I chose epsilon to be arbitrary because I wanted to prove this is uniformly continuous, right? So for that I need that for any epsilon this thing should hold, that this should be less than epsilon, right? So I chose any epsilon arbitrary. Now, so this has been chosen now. Okay, this is arbitrary but it has been chosen. Now for this epsilon I'll get a delta 0 since g is continuous, uniformly continuous. Now for this delta 0, okay, so now I can say that this delta 0 is a positive number. So now for that delta 0, now this will act as an epsilon kind of for this f. So for this epsilon which is equal to delta 0, there exists a delta 1 such that this thing happen. Okay, is this clear?
Yes, sir.
Okay. Okay, so you just have to play with this and then you can clearly see like it's not a difficult thing to establish this result. It's just the use of argument properly, that's it. Okay, so now let's talk about this one. So it's given that you have to check that if a square function, like if a square is continuous, then can you say that f is continuous? What do you think?
It can be taken as a composition of f and f.
Not exactly. Like this is product. F square is f times f. It's not the composition. So how can you? So you see, suppose f of x is sine x. Okay, so f composed f is sine of sine x, but f square x is sine square x. These are two different things. Okay, so composition is not same as a square. Square literally means like just taking a square, like just like real numbers, that's it. So now here the question is that if f square is continuous, can you say that f is also continuous? F has to be continuous. We know other way around, that if f and g are continuous, then f times g is continuous. In particular, if f is continuous, then f times f is continuous. But this is something converse, that suppose f times f, which is f square, is continuous, can you say that f is continuous? You must have seen examples for this. It's very easy example. So this is false, right? This is a false statement, and this is like you can take a function like this, maybe f(x) equal to 1 if x belongs to q, and minus 1 if x belongs to q complement. Clearly this is discontinuous, right? We have a jump discontinuity. It is oscillating between 1 and minus 1. But if you take f square of x, this is going to be 1 for all x in R, right? So this is discontinuous, but f square is continuous. So clearly that statement is false. Okay, now let's come to the third one, that if f cube is continuous, okay, can you say that f is continuous? This is quite interesting, and here you can use the composition stuff over here. Okay, so this is true, so I'll just prove this maybe. Simply write this is true, and the proof goes like this. Okay, so suppose like okay, so let me write this as h of x, let me call it as f cube x as h of x. So I'm defining this new function h. Okay, and the next function I will define it as, let's say, g of x, which is x raised to the power 1 by 3. Okay, so what we have is, it is given that f cube is continuous, so h is continuous, correct. G, we already know this is a continuous function, so this is continuous on R, this is continuous on R. I hope it's given to be R. Okay, it's defined on the whole real line, so this is also continuous on R. Now you take composition. Okay, so let's see if I take, because see, f cube is going to map to R, so you can understand that this composition makes sense. Okay, I'm not writing precisely, but you can understand that because this x 1 by 3 is going to take all the real values. Okay. Anyway, so like g composed h, if I do, so what is that? So this is g of hx, correct, and this is nothing but g of h of x is f cube x. Okay, and this g of f cube x is nothing but f cube x and then power 1 by 3, and this turns out to be f of x, correct. So now what I know is h is continuous, g is continuous, so this composition is continuous, and this tells you that is f is continuous. Okay,
Same proof for f. Why can't we apply the same proof for
because see here,
f square, sir?
yeah, here you can see, here you can make, okay, maybe I can write one more line. So see, suppose let's say I'll copy this, but if I try to copy this, when we have to make sense of this composition, right? But when you say, let's say h of x is f square x, okay, let's try to do that, and this g of x should be x half, correct. Now if you try to define, sorry, g of h of x, just a second. So let's say this domain of this would be R, and the codomain would be 0 to infinity, right? Here you can, okay, so here so it's from 0 infinity to, let's say, 0 infinity, correct. Now here if I define this function, I'll get f of x, correct, in the same way, and here the domain would be 0 infinity, sorry, it would be from R to 0 infinity. Can you see it?
Yes, sir.
But my initial f is from R to R, let's say. So these two functions are different. So maybe I can say this is how to write this, just a second. But you understand this function. Okay, so let me write it in this way, then I think it should be proper. So this is from R to 0 infinity, okay, such that g composed h of x, if I evaluate it, it is going to g of hx, okay, and this is going to g of hx would be g of f square, and this is f of x. Okay, so this function g composed h matches with f, okay, but its domain, codomain, is going to be 0 infinity, right? So in this case, maybe the example what I give, you can think that this f of x is taking -1 and +1 value both. But when I define this composition, you see how it is defined. This h is from R to 0 infinity, and then this is hx. So now hx is in 0 plus infinity. Now this hx, this x power half is, if you do, you will get f of x, but this is something which is positive and the output are also coming to be positive. So the codomain of this function g composed h and the codomain of f are completely two different sets. So now these two functions are not equal, right? So this is, maybe I can say this, that f is equal to j. For this you have to make sure that the domain of f should be equal to domain of g, the codomain of f should be equal to codomain of g, and f of x should be equal to g of x for all x in the domain. This is the definition of equality. So these two functions although look similar, but they are completely two different functions because their codomain are different. Okay, then now let's move to the next problem. Okay, so this is done. Now the question is that sine x square and cos x square are uniformly continuous on R. Is this a statement? Is this true or false? What do you think? So we know that they are continuous, right? Because this is a composition of two continuous functions. Sine is continuous, x square is continuous, so their composition is continuous. So continuity is not a problem, but the problem is that, but the question is that, is it uniformly continuous? What do you think? Do you have any answer to this? Have you seen such thing?
Not uniformly continuous, sir.
You know how to argue? Okay, so what you are saying is actually correct. This is a false statement. But do you know how to prove this? Okay, so let's start the proof. So the proof, actually you can do it by contradiction. So we'll assume that, okay, let it be uniformly continuous, and then again the same thing, like how do we deal with sine function and cosine function? We just look at the two different points where it becomes zero in some sense, right? Or it be like just using the property that n pi and n pi plus pi by 2 kind of stuffs, we can try to get a contradiction. Okay, so let's see how the proof goes. So at first let us assume that, if possible, let us assume that sine of x square is uniformly continuous. Okay, so we have assumed this. Then what you can do is, then for we'll just write the definition. Then for epsilon, okay, we'll see what epsilon we can choose. So let's start with epsilon greater than 0. There exists delta greater than 0 such that this f of x minus f of y is less than epsilon if mod of x minus y is less than delta. Okay, now over here, to contradict this statement, what we need is that we want the points to be close, but this function's value should be very large. Okay, so we have already seen like this kind of thing. I remember that I have once told you. So I'll just try to recall you something. I also just forgot, like how did I mention it to you. But it's like, suppose like you have 2 points, so n pi plus pi by 2 and n pi. Okay, so now we know that if I take the difference, it is going to be pi by 2, correct? So if I subtract this 2 point, so the difference of these 2 point is going to be pi by 2. Okay, but if I take root, okay, then you can see that for large n this is going to be very small. Okay, that anyway I'll prove it. But this you can make it very small. Okay, but their functional value, if you see, just because of square, you can see that one will take the value 0 and the other will take the value 1, correct? So this functional value will be always equal to 1, while these points will be very close for large n. Okay, so this is how the argument goes. So now I'll write it precisely. Okay, so this is why I can take epsilon to be 1. Okay, so now I can write epsilon, let's say epsilon to be 1. Okay, so then this is the definition that from uniform continuity I have this definition. Okay, so let's say this is star. Now let x equals to root n pi and y equals root n pi plus pi by 2. Okay, then mod x minus y, if I do, I'll get, if I rationalize it, I'll get n pi minus, so I'll get minus pi by 2. Okay, but anyway mod is there, and in the denominator I'll have n pi plus root n pi plus pi by 2. Okay, so let's say this is just pi by 2, and this is what I have. Now you can clearly see that this quantity, okay, I can get rid of that. So maybe I can say that this is pi by 2, because this is always going to be greater than equal to, or you can also think this is greater than equal to 0. So I can replace this by 1 by root pi and root n, correct? And this is nothing but, so this root pi will cancel with this one, so I'll get root pi here. Okay, and this is, again you can say that this is less than 1, so this is less than 1 by root n, I can say, correct? And this I can make it less than delta for large n, so that's what I will write now. Okay, so this is less than delta for n greater than equal to delta square, right? So this is something that we can choose. So for large n I can make this x and y, so maybe I can say, so you can understand that this x and y are depending on n, but now I'll choose some capital N. Okay, so how should I write? Okay, so the proper answer would be like this, if you want to. So maybe this is one way, the other way would be like just directly kind of back calculation. So you can say that let choose capital N in natural number such that this n is greater than equal to delta square. Okay, then now choose x equals to root of n pi and y equals to root of n pi plus pi by 2. Okay, then you can see that x minus y, which is less than 1 by root n, and this is, okay, I think I have written here wrong, 1 by delta square should be there, no? Otherwise this will be also very small. Okay, yeah, so 1 by n, which is less than delta. Okay, and but mod of fx and fy, if you try to look at the difference, you will have sine of x square would be n pi, which is 0. So sine of n pi minus sine of n pi plus pi by 2, and this is equal to 1. Okay, so you can clearly see my x and y are very close, I mean less than delta x minus y, but fx minus fy is equal to 1, so it's not less than 1, correct? So this contradicts star. Okay, hence sine x square is not uniformly continuous. Okay. Okay, so on R it's not uniformly continuous, but if you take a bounded domain, then it will be uniformly continuous. That you know already, right? That any continuous function on a compact set or closed and bounded interval is going to be a uniformly continuous function, right? That I hope you already know. So it's, the main thing is about R, it's not uniformly continuous on R. Okay, so in a similar way, similarly you can show that cos of x square is not uniformly continuous. The same logic would work. Okay, so now let's come to this next problem. Okay, so this question says that suppose f is a function from an interval to rationals. Okay, so the codomain of this function is rational number. Okay, so if you assume that this is a continuous function, then you have to say, you have to prove or disprove that f is constant. So what do you think? Is it true that any continuous function, so the statement could be any rational valued continuous function is constant? So is this true? That any rational valued continuous function is constant. Are you able to understand the question? That if a function is just taking rational value and it is continuous, then the function has to be constant. So f can be any, so it says that fx will be some p by q for all x in AB. This is what this statement is saying, that if f is continuous and the codomain is rational. Do you see, like, any idea are you getting, or any feeling like whether that will be true or false? Okay, so do you know this property, that this intermediate value property of a continuous function?
Yes, sir.
So suppose that it is not constant, okay, then it will take two values, let's say rational q1 q2 like that. Now between these two rationals there will be irrational number as well. Yeah, but
Yes, sir.
it says that the codomain is going to be rational, so then that will violate the intermediate value property, right? Okay, so this is a false statement. Okay, maybe I can write one or two lines. Okay, so suppose okay, so if possible let f be non-constant. So I mean, so that means that there exists x1 x2 in AB such that f of x1 equals to y1 and is not equal to y2, which is f of x2. Okay, where this y1 y2, so obviously this y1 y2 y1 y2 is belonging to rational number. Okay, now we know, so how should I write? So okay, so maybe I can say, since y1 is not equal to y2, there exists some y0 in irrationals such that y0 belong to q complement, such that y0 lies between, so how should I say, so maybe without loss of generality you assume that y1 is less than y2. So this is by without loss of generality. So you know, like, without loss of generality means you can assume one of the cases. Now if y2 is also less than y1, then the same thing would work, like it's not so just because I want to write that y0 belongs to y1 comma y2, I am just writing in this way. Okay, so there is no problem taking y2 or y1, like, because they are symmetric kind of thing. Okay. Okay, so such that y0 belongs to, so between these 2 points there will exist some irrational number. That's all what I am saying. Now since f is so, okay, so now that this is complete, now as f is continuous, so by intermediate value property there exists x0, okay, in between x1. So let me say here also that x, okay, or maybe I can write in words, x0 lying between x1 and x2 such that f of x0 is equal to y0, which belongs to q complement, and this is a contradiction, but codomain of f is equal to q, hence f must be constant. Okay, so that's the proof. Okay, so now let's quickly move to the next problem. Okay, so this is a function. It's similar to this, what you have seen for this Thom's function, that what we have discussed in the last session, I guess, maybe last to last, I don't remember, but it's similar to that function. So it's 0 when x is equal to 0 or when x is irrational, and otherwise it's 1 by q raised to power 3 if my x is a rational number. Okay, so here this q is a natural number, okay, and GCD of pq is 1. So the question is about the differentiability. Okay, so whether this function is differentiable at 0 or not. So let us check that one. You can clearly see, okay, so no, you cannot. So let's try to check the differentiability at 0. Okay, well, so for differentiability, like this is the definition, right? So f prime, okay, so differentiability means that this limit x tending to c, f of x minus f of c upon x minus c should exist, then f prime of c would be this limit minus f of c upon x minus c, right? So what we have to show, that the limit, so since we want to prove the differentiability at 0, so c is equal to 0, so I want to check that the limit x going to 0, f of x minus f of 0 upon x minus 0. So we have to look whether this limit is exist or not. Okay, so let us try to see that. So f of 0, we know that it's 0, so what we have to check is that this limit x tending to 0, f of x upon x. So if it limit exists, then we'll say that f is differentiable at 0, and the limit value will be the value of derivative at that point, I mean at 0. Okay, so let us try to check this one. So let us try to see how this function looks like, fx upon x. Okay, so fx upon x is basically, it will be 0 if x is irrational, right? So it is going to be 0 if x belong to q complement. Okay, so we are not talking about x equal to 0, because at x equal to 0, this will be, I mean, here we in the denominator we have x as well, so we are not talking about x equal to 0, because we are just talking about the limit, so we don't need to bother about it. So if my x belong to q complement, then this is the value it's taking, and it is equal to, so it will be like this, 1 by q and then p by q divided by, so you'll have q by p if x is equal to p by q, and again the same thing, q belong to natural number, p belong to z, and GCD of pq is equal to 1, right? So now this is nothing but 0 if x belongs to q complement, and it's 1 by p times q square if x is equal to p by q. Okay, with the same conditions. Now over here, what you have to make sure, we are looking at the limit as x goes to 0, right? So in this case anyway, this is not a problematic case, because this is always less than epsilon, right? So this, it seems that because of this case, it seems that if this limit exists, it has to be 0, right? Because this is what we are looking at. So here it's always 0, this ratio. Okay, so this is always going to be less than epsilon, that is for sure. Now to make sure that this is less than epsilon, we have to choose this x in a close neighborhood of 0, right? And this is what we want, because we are looking at the limit. Okay, So maybe I can write it in this fashion, that if my this x, if p by q minus 0, okay, if I assume that it is less than delta, okay, I'll see what the delta I need to choose. Okay, depending on epsilon we have to choose delta. So suppose I assume that this is less than delta, then what will happen is, then this 1 by p times q square. Okay, so this is nothing but I can make it, so I have to somehow bring p by q into the picture, right, so that it becomes sorted. So what I can do is, maybe, so let me see, so I can make it, so let's separate it out, 1 by p and then 1 by q square. Sorry. Now you know that this p, okay, this p is an integer, so mod p is always going to be greater than 0, and p, okay, so p is non-zero, right, we are excluding the case when p is 0, so p belong to z minus 0. So maybe here also I can write it, I think I missed it here. So here this p belong to z minus 0, maybe I can do this correction. This is z minus 0, because when p equal to 0, that is already considered here. Okay, so this would be a small correction here. So p belong to z minus 0. Okay, now since p belong to z minus 0, I can say that mod p is always greater than 1. So I can say that this 1 by mod p is less than 1. Correct? Similarly with q. So ultimately what I can say, this is less than 1 by mod q. So I'll keep 1 q over here, and the rest I'll just make it less than 1. Okay. Now what you can do is, here, okay, from here you can observe that this 1 by q is less than delta by mod p, right? So maybe, or you can do here itself, like it's not a problem. So maybe let me write in this way, that would be better thing to write. So maybe I'll write 1 by p by q in this fashion. So let's say I'll multiply p and divide by p. So I'll have p by p square q square, and this is nothing but so p by q I'll make it separate, and the other would be 1 by mod p square q. Okay, and this I know this is greater than 1, so I can say this is less than mod p by q. Okay, because this part 1 by this thing is less than 1. Okay, now this I know this is less than delta, so if I choose my delta equal to epsilon, I am done. Then if I make this p by q is in the delta neighborhood of 0, then this is less than epsilon, right? And this proves, okay, so this is, so what I can write, combining all these stuffs, what I can say is mod of fx upon x is less than epsilon if mod x is less than epsilon, right? This is what I can say combining these two things. So what, oh sorry, okay, so what this proves, that limit x tending to 0, f of x upon x is equal to 0, and this limit exists, and this implies that f prime at 0 is equal to 0. Okay, so this function is differentiable at 0, so this first option is correct. Second, no, okay, so now let's talk about differentiability at 1. Okay, so now you can see here, maybe, okay, let me write here itself. So first let us see what is f of 1. F of 1 by definition it's going to be 1, correct? So f of 1 is equal to 1. Now if I choose my rational number, so sorry, what I am saying is that for this one, there exists a sequence, so maybe I can write, consider a sequence, this is by density, that I will consider a sequence in q complement, so let me say xn, consider a sequence xn such that xn converges to 1. Okay, suppose I choose this one, so there is a reason why I am choosing in q complement, you will get to see. So if I consider this, then what I can say is that f of xn is always going to be 0 because it's in the q complement, correct? And such sequence existence is guaranteed by the density. Okay, so we can consider such sequence, and we know that f of xn is 0. So f of xn minus f of x upon xn minus x, if I do, then this is going to be minus of fx upon x. So minus of f1, sorry, I am talking about derivative at 1. So this is xn minus 1, and this f1 is nothing but f1 is 1, correct? So this is what I am getting. Now you can clearly see as n goes to infinity, this is going to infinity because xn converts to 1, so this denominator is going to 0, correct? So this whole thing, okay, I cannot even say goes to infinity. Maybe for that I'll have to take mod, because xn could be greater than 1 or less than 1. So that's, so let me take mod for now. So this mod will go to infinity as n goes to infinity because xn goes to 1. Okay, so what does this tell you? This tells you that this limit x going to 1, f of x minus f of 1 upon x minus 1 does not exist, because we have found a sequence for which it is blowing up to infinity. I mean, if you take modulus, obviously. So because if this exists, then the modulus limit will also exist, and hence that cannot go to infinity. Okay, so you can argue from there that you can conclude that this limit does not exist. Okay, so this proves that f is not differentiable at x equals 1. Okay, is this clear? Okay. Okay, so I think we have already done this kind of problem when we were dealing with proving convergence of sequence and all thing, but those things were more with natural number. But I think I gave you idea like how to prove this kind of inequality, right? So we just, so how, let me just write. So to prove this, so what we'll do is, so we'll just subtract this with this function, right? So with log, so I can define this fx as log of 1 plus x minus x upon 1 plus x. Okay, now you know that from here you can clearly check that f of 0 is going to be 0. Okay, and this is for x greater than 0. So this, I am defining this function. Okay, so I think I can put x equal to 0. Okay, I understood. So if I put x equal to 0, then I will have to put x, I mean here equality as well, because in that case everything will be 0. So let's not go with that. Okay, but over here I can say that f of 0 is 0. So maybe I can define here x greater than equal to 0. So this is my function what I am defining here. Okay. Now you can check that if I take the derivative of this function, what I get is 1 upon 1 plus x minus, so I can write this is 1 plus x square, and this is 1 plus x minus x, right? So what will be this? So this is 1 by 1 plus x minus, so this x will cancel with this one, so minus 1 by 1 plus x square. So this is x upon 1 plus x square, correct? Now you can clearly see that this is positive and this x is always greater than equal to 0. In fact, this is greater than 0 if my x is greater than 0, and this is the domain. Okay. Oh, sorry. So for x strictly greater than 0, my derivative is greater than 0. So this would imply that f is strictly increasing on 0 comma infinity, correct? And this would mean that f of x is greater than f of 0 if x is greater than 0. And this will tell you that this log of 1 plus x, because this is equal to 0, right? f0 is 0, so a log of 1 plus x is greater than x upon 1 plus x for x greater than 0. Okay, in the same way, what you can do is, to prove this one, you can define g of x to be log of 1 plus x minus x. You can define g of x to be log of 1 plus x minus x. Here you can check that g prime x would be 1 upon 1 plus x minus 1, and this will give you x minus x, minus x upon 1 plus x. And you can clearly see that this is going to be negative if x is positive, and this will tell you that g is strictly decreasing on 0 infinity, and this will tell you that g of x is less than g of 0 if my x is greater than 0, and this will give you that log of 1 plus x is less than x for x greater than 0. Okay, so these inequality, like, you can easily prove, at least for this function it's very easy. You can do it in this way. Okay, I hope this is clear to you. Okay, so now let us consider this function f of x is given by in this way. So you have to check the differentiability of this function. That is the first thing. The second thing is that how, so we will check, okay, so at first we have to get to the derivative, okay, if it is differentiable or not. And the moment we are able to find the derivative, so it's clear, like from here, although it's clear that it is differentiable for 0 in open interval 0 infinity, that is anyway fine, right? Sorry, so here 0 1, or I can say minus 1 comma 1 minus 0. So the only problematic point is 0. So except 0, it's everywhere, it seems that it's differentiable, right? Because it's just a polynomial function with sign. I know both of them are differentiable, so the product would be differentiable. Okay, that is not an issue. The main problem is at 0. Okay, so for 0 we have to check whether it is differentiable or not. Okay, now from here f, I'll get f prime. Okay, now we have to check, so we'll see how f prime looks like, and then we'll see that if f prime is continuous at x equal to 0 or not. So when I say to check continuity, that means that f prime 0 should make sense. That is the first thing. Okay, if it makes sense, then we'll see, that means f is differentiable at 0. Now if f is differentiable at 0, we have to check that the f prime, the derivative function, is it continuous at 0. Okay, so these are the two questions that we have to answer here. Okay, so we'll see how to prove these things. Okay, so let's start with the first part. So first part asks us to prove that it is everywhere differentiable. Okay, if alpha satisfies this property, that alpha is strictly greater than 1. Okay, so let us try to see that. So if, so okay, I can write one line that clearly f is differentiable on minus 1 comma 1 minus 0. Okay, and f prime of x would be given by, so maybe you can calculate. Okay, just a second. Okay, I think I am here. I think x beta, okay, I should mention here that my beta is greater than 0. Okay, because if beta is less than 0, then that would mean that it is sine of, okay, in that case also it's differentiable, that is not a problem. Okay, that's not a problem, but what I was, yeah, it's fine. Okay, so now let us write the derivative. So f prime x would be x raised to the power alpha, and then the derivative of sine would be cos. So cos 1 by x beta, and then you will have beta x beta minus 1 plus alpha times x alpha minus 1, and then sine 1 by x beta. Okay, so I can take x raised, okay, let's just combine this up. So I'll have beta x raised to the power alpha plus beta minus 1 cos of 1 by x beta. Here I'll have alpha x alpha minus 1 sine of 1 by x beta. Okay. So this is how my derivative will look. So this is when x is not equal to 0. Okay, so now we have to check the differentiability at 0. Now for that, what we need to make sense of that this limit f of x minus f of 0 upon x minus 0, this limit should exist. Okay, x. Okay, so this you can see that this can be further simplified as f of x. We know this is x alpha sine 1 by x beta. F of 0 is given to be 0, so let's not worry about this. So that is 0, and then you have x here. Okay, now this, why I'm writing h always. So this is limit x going to 0. Here I'll have x alpha minus 1 sine of 1 by x raised to power beta. Okay, so this is what we have got. Now over here you can clearly see that if alpha minus 1 is equal to 0 or less than 0, in that case this limit will explode to infinity. So the first thing is there are two cases. If my alpha minus 1 is equal to 0, in that case this will be missing, this will be 1, right? So I'll have just sine function. Okay, and as x goes to, so this is, the limit will not exist at all, because it's going to be oscillatory. It is not converging to a particular point, because sine function takes all the values between 1 and minus 1, and that's how it will behave. But if, and this is the first case, and if alpha minus 1 is negative, okay, then I'll have this 1 by x 1 minus alpha kind of thing, correct? And as x goes to 0, this will blow up to infinity if x is positive, right? And if x is negative, this will go to minus infinity. Okay, so in that case this is unbounded, so again the limit will not exist. So for this limit to exist, so this limit exists, how should I write? Exists if and only if this alpha minus 1 is greater than 0. Okay, so if, and okay, so and if alpha minus 1 is greater than 0, this limit x tending to 0 f of x minus f of 0 upon x minus 0 will be equal to 0, right? Because due to this thing, sine is bounded, this will go to 0, so this limit will be 0. So hence f prime 0 is equal to 0 if alpha minus 1 is greater than 0, right? So this proves the first part, that it is differentiable. Okay, so everywhere, so for 0 I need this condition, but other than 0 it is differentiable, so there is no question at all. Is this fine? Okay, so now let us see how this f prime function looks like. So this f prime x is given by this beta, so let me just copy this up. Okay, this is when x is non-zero, this is 0 if x is equal to 0, right? So now we have to check the continuity, right? So it says that the second statement says that if this condition is there, then f prime is continuous. Okay, so let us see. So what is the condition? That beta less than alpha minus 1. So 0 less than beta less than alpha minus 1. If this is there, then the limit x going to 0 f prime of x, if I look, so you see that due to this condition alpha minus 1, okay, then how can I say, just a second. So one thing is clear, that this alpha minus 1 is positive, so this will go to 0 as x goes to 0. But this one, did I do some mistake? Okay, sorry. So here it would be minus beta, right? And here also there will be minus sign, because just a second. So here minus, here also there will be minus. Okay, so I'll have this one, so minus here, and here also minus. Okay, so now this quantity is always, this is also positive, right? Alpha minus 1 minus beta, this is greater than 0, so this quantity will also go to 0 as x goes to 0, correct? So the limit of this function will be equal to 0, okay, under this situation, and this is nothing but f prime at 0, right? So this proves that f prime is continuous at x equal to 0, okay? And at others point it is already continuous, we don't even need this condition, because it's just polynomial and cos, polynomial and sine, so it's continuous at the other points. Okay, now let us come to this condition, that if alpha minus 1 is less than equal to beta, then the function will no longer continuous. So this is the condition. In this condition you can clearly see that this limit will not exist, this one, it will go to infinity, okay? So the limit, maybe I can say that the limit x going to 0, x alpha minus 1 minus beta cos 1 by x beta does not exist, okay? Okay, so this will not exist. So from here, okay, so maybe I can write one more line also, but okay, let me write in terms of point. So limit x going to 0, this x alpha minus 1 sine of 1 by x beta, this is 0, okay? So you see one limit is existing, so this limit goes to 0, but this limit does not exist. So from here you can say that the whole limit will not exist, because if the limit exists, then you can subtract this one. I think I already discussed in last session. So suppose this limit of this whole sum exists, okay? If it exists, you also know that the limit of this exists, so you can subtract this with that one, then you will get that the limit of this function is also exists, but we know that the limit of this function does not exist, okay? So I'll just write one line, but you know how to argue. So this implies that the limit x tending to 0 minus beta, so let me just copy it from here. Okay, so this does not exist, okay? So that function, the derivative cannot be continuous, okay? So this proves that f prime is not continuous at x equal to 0, okay? So we have proved all the three questions that was asked here. So now let's move to, I hope this is clear. Do you have any doubt? Okay, now let us look at this problem. So this is a polynomial, okay, and you have been asked about the roots of this equation. Okay, how many root does this polynomial have? So
One real root, sir.
one real root. How can you prove it?
This is the odd degree polynomial.
Okay, so are you saying that the odd degree polynomial will have just one root? Is it?
At least one real root.
Yeah, at least one real root is there, correct. Okay, so let us try to look at this particular equation, whether that will have how many roots it has. So we'll see that, let us say that this is f of x is equal to x of 15 plus 7x5 minus 5 equal to 0. Okay, now okay, one more thing what I can do is, okay, I think in this case what your argument is, it might be true because both are odd. In that case I think it could be, but I don't know how to argue. But anyway, like, we can think in this way. So this is the function, okay, so we want to look for the roots of this function. Okay, this is a polynomial. So let us try to see the derivative, how it behaves, whether it's increasing, decreasing, or what kind of property it has. So you can see this is 15x14 plus 35x4 and then 0. So this would be x4, I can take common 15 x raised to the power 10 plus 35 equals to 0. If I do, okay, so let's not put 0. So what I can see that this f prime of x, okay, is equal to 0 if and only if x is equal to 0, right? Otherwise it's going to be positive, right? So what I can say is f prime of x is greater than 0 for x greater than 0. Okay, so see, it is this particular case where both the orders, where both the powers are odd. What you are saying is true, that it will have exactly one root because this function is going to be strictly increasing. Okay, that means it is going to be 1 1. Okay, that means that this fx will take value alpha. Okay, so for different points, I mean, there could not be 2 points f of x1 such that f of x1 f of x2 is equal to alpha, so in particular 0. So there could not be such scenario because it's strictly increasing. Okay, but this is possible here because both of the orders are odd. Okay, but in general for odd polynomial, odd power polynomial, you cannot say that it has to be have just exactly one root. Okay, you can say just that it will have at least one real root. That's all you can say. Okay, so this is what we have, that f prime of x is greater than 0 for x greater than 0. So this means that okay, in fact for x in r minus 0, why do you need, okay, so in here also it's strictly increasing in this region, right? Here also it's strictly increasing. Okay, so from here you can clearly see that, I mean, how should I say, this tells you that it is 1 1 kind of function. Okay, so this is the first thing. Now how do we guarantee that 0 will be attained? Okay, for that you can see that f of 0 you look, then that is going to be minus 5. This is less than 0. And if you look at f of let's say, what value can I take, but 2, let's say, okay, f of 2 you choose, then this is going to be 2 raised to the power 15 plus 7 2 raised to the power 5 and then minus 5. This is obviously positive quantity, right? So you can clearly from here you can say, by, because this is a continuous, right? So this is a continuous function because it's a polynomial. So from here you can say by IVP there exists x naught belonging to 0 comma 2 such that f of x naught is equal to 0. And so this tells you that there exists one real root, but due to this fact, okay, this fact that it is strictly increasing, that means it is okay. So maybe I can say from here this implies f is strictly increasing. Strictly increasing on R. So you can say from these two facts. So from here you can also say that f is 1 1, maybe f is 1 1. So this, okay, maybe you can use this reasoning afterwards. So just a second. Yeah, so maybe I'll just cut this. Reason this first, that there exists a 0. Now let's say that we have this argument. Okay, now from here it says that this implies f cannot have more than one root. Okay, so f has exactly one root. Okay, so exactly one real root. Okay, so now let us come to this next problem. So again we have to talk about the roots. So here you have this kind of equation. So do you know the answer of this problem?
One real root, sir.
One real root. Okay, so how do you prove this one? Any idea? So one thing it's clear, I guess. Okay, so just a second. Okay, you can clearly see that x equal to 1 is a solution, right? So I mean this is quite easy. One can clearly see that one root you can explicitly find. X equal to 1 is going to be one solution. Okay, leave it. Yeah, so now so you are saying that it has exactly one root. One root we can clearly see. So this option is anyway not going to be true. Okay, so now let us try to find that whether it has exactly one or more than one. Okay, so like this, using this kind of equations you can handle it in the following way. So maybe so see, the main thing is that you have to somehow go to some, if you really want to prove that it has exactly one root, then it will have some increasing or decreasing kind of property, right? So we have to somehow go to the to test the derivative. Okay, that this is what we have done above. So we'll try to do in the same spirit. Proving that it has one root is very easy. You just try to, so maybe you can do it in this way as well. So fx you just take 2x plus 5x minus 7x, right? So f at 0 you can clearly see that it is 1, which is greater than 0. Obviously what you can do, you can find some large number, because you see 2 raised to the power, let's say, how can I choose? So let's say f to 3, let's say the 2 raised to the power 3 would be 8, 5, 5, 5, 125, and 7, 7, 49 times 7, what will be the value? Clearly you can see that this is going to be negative, right? So clearly you can say that there exists one root. But now you have to talk about differentiability and see that this function is increasing or decreasing, something like that. Okay, so this is how we will try to prove. So this getting one root is very easy. You just have to try to see whether at some point it's becoming negative and at some point if it's becoming positive and the function is continuous, then you know by intermediate value property that it will have a 0. Okay, but now we have to check whether it's it has exactly 1 or not. Okay, so maybe we can try to continue with this function. So we consider f of x as, let's say, 2 raised to the power x plus 5 raised to the power x minus 7 raised to the power x. Okay, now you can clearly see that here it was positive and then it was negative, so it seems that it should be decreasing kind of function. Okay, so let us try to look at the derivative. So it will be 2x and then log of 2 plus 5x log of 5 minus 7x log of 7. Okay, so how you can clearly, okay, so what I can, you can clearly see that this power of 7 will, okay, but here I don't know, just a second. I know ultimately it will become negative, but how do you argue this? So here I can write, okay, I cannot do it 2 plus 5. Okay, so maybe let's try with this other function. Here I can say 2 plus 5x, but again I cannot compare it. Okay, so let's try with this function then. Just divide it. Okay, so you have to solve for this. You can take 7x in the left hand side. So you can consider this function maybe 2 by 7x, because this one is easy in the sense, I'll tell you why. 5 by 7x. Okay, so you see, when you here what we were getting is log 2, log 5 and log 7, right, and with some power. But here we know that this log is positive, this log is positive, this log is positive, but here I had minus sign, and saying whether it will be positive or negative in the whole domain was quite difficult. Okay, and I cannot guarantee that also, that whether it will be strictly greater than 0 in the whole domain or not. But here I think it would be easier, as if you take f prime x, you see know that this is 2 by 7 x, and then you have log 2 by 7, and you know that this is negative. Okay, the second thing is you have 5 by 7x, and then you have log of 5 by 7, again this is negative, right? And this 5 by 7 raised to the power x is always going to be a positive quantity, right? So what we have is this whole quantity is less than 0, so this tells you that f is decreasing, strictly decreasing, and this tells you that f of x is less than f of, okay, so sorry, why do I need this one? So this tells you that f of x, so maybe I can write in words. So there exists only one x in R such that f of x equal to 1. This is another way of saying that it is 2x plus 5x is equal to 7x. Right? Okay, so the first thing is that we have to say that 1 is in the range, and for that what you can argue what I said earlier, maybe this argument you can say. So this implies there exists one x in R such that f of, okay, so let me say this is g of x, such that g of x is equal to 0. This tells you 2x plus 5x equal to 7x. Okay, so maybe you can compress this up. Ah, shit. This is g of 0 to 1, g of 3. Okay. Okay, now let's move to this problem. So here you have been given that this function f is continuous on closed interval 0 2, and it's twice differentiable on this open interval 0 2. So you have to, and these three things you have been given, that f at 0 is 0, f at 1 is 1, and f at 2 is 2. So you have to prove that there exists a point C where the second derivative is equal to 0. So whenever see these kind of problem, if you see that where you have been given that it is continuous on the closed interval, differentiable on open interval, then you have to understand that maybe you can solve this problem using some mean value theorem, maybe Rolle's theorem or Lagrange's mean value theorem. Okay, so we'll try to solve that using Rolle's theorem, but you have to do a bit of change. So you have to use this fact also. So you cannot directly use this Rolle's theorem directly on f, because for Rolle's theorem you know that at 2 points at the end points it should match, then there exists a point c where the derivative becomes 0, right? Or if you want to use Lagrange's, so you have to have the values at 2 points should be same. Okay, so what you will do over here, you can see that f at 2 is 2, f at 1 at 1, and f at 0 is 0. So if I define my function g, okay, so I am considering a new function. So consider a function g given by g of x is equal to f of x minus x, then clearly the same property will be true, that g is continuous on 0 to g is differentiable on open interval 0 to. Okay, and these property f0 f1 at 1, f2 at 2 is f at 2 is 2. Using that, what you can say that g at 0 is 0, g at 1 is 0, and g at 2 is 0. Now using these two things, okay, and also obviously these two conditions, so using Rolle's theorem, what you can say that there exists some c1 in 0, 1 such that g prime at c1 is equal to 0. Correct, because they are taking the same value. Now using these two, you can say that there exists c2 in 1, 2 such that g prime at c2 is 0. Okay, so these are by Rolle's theorem or Lagrange's mean value theorem, just I write mean value theorem. Okay, you are getting these two things. Now again, what you can say that this g prime is again differentiable, and this g prime is again continuous on this 0 2. Okay, so okay, I think that is somewhat. So what you can say here in the next line, that g prime, if I restrict to c1 to c2 to this whole R, okay, so I am restricting this g prime, so maybe let's say I am defining this g bar, okay, such that g bar of x is equal to g prime. So this is continuous on c1 c2, right, and it's differentiable on c1 c2, and g prime at c1 and g prime c2 and g prime at c1 is equal to g prime at c2 is equal to 0. Okay, then again you can use the, so hence by Lagrange's mean value theorem or Rolle's theorem, there exists some c in c1 c2 such that g bar prime c is equal to 0. This implies that g double prime at c equal to 0, and this implies that g prime is nothing but f double prime, right? You see, because x will vanish after taking double derivative, so this implies f prime at c is equal to 0. Okay, so I hope you understood how I'm writing this continuous on c1 c2, because it was given that f is double differentiable, so the first derivative is also differentiable, that means the first derivative is also continuous. Okay, so now let's move to the next problem. Again similar kind of stuff. So here you have been given that f from 0 to is continuous on this closed interval, differentiable on 0 to, but here there is a small change, that f at 0 is 0, f at 1 is 2, and f at 2 is 1. Then you have to prove that f prime at c is equal to 0. Now how to solve this one? Again, when I said that it's, if you see problem in this fashion, that it's continuous on closed, differentiable on open interval, then you have to use this mean value theorem kind of stuff. Okay, so what you can say here is, you can argue in this way. So I'll try to use this f0. So I'll use this by Lagrange's mean value theorem. So what I can say is, there exists some c1, okay, belonging to this 0 comma 1, such that f prime at c1 is equal to f1 minus f0 upon 1 minus 0, and this is nothing but f1 is 2 and this is 0.
Okay. 1 minus 0, sir.
Oh, sorry. This is 1 minus 0. Yeah. So what you have is, this is 2. Correct? But then okay. Now again, by LMVT, I can say there exists some C2 in 1 comma 2, such that this f prime at C2 will be equal to f2 minus f1 upon 2 minus 1. Now f2 is given to be 1, f1 is given to be 2, and then you have 1. So this is minus 1. Now I think it's obvious. This is positive, this is negative, and here you don't need intermediate value property, right? Because f prime is not given to be continuous. You see here it's just given that f is differentiable. You don't know that whether f prime, the derivative, is continuous or not. So you cannot use the intermediate value property, but you have something, right? You know something like intermediate value property kind of stuffs for the derivative. So do you know this Darboux theorem? So the Darboux theorem says that the derivative always have this intermediate value property for a continuous function. If it's differentiable, then the derivative will have this intermediate value property. Okay, so therefore by Darboux theorem, there exists some C0 belonging to C1, C2, such that this f prime at C is equal to 0. Okay, so here we cannot use the same kind of argument, but over here we had one disadvantage, that at one point we were getting this difference to be positive, and on the other one it was negative. Okay, so now let's look at this problem. Okay, so this is I would ask you one thing, that can you find some relation between these two things? So see, okay, so let me first tell you the question. So the question is like, this is the polynomial, nth degree polynomial, and the coefficients are satisfying this property. Okay, then you have to show that this px will have at least one root. Okay, my question is that can you see some relation between these and this? So how can I say? Okay, I don't think that it would be easy to guess, but okay, let me tell them. So suppose you define this function. So suppose you integrate this p. Okay, so I'll define this f of x maybe like this way. So let's say it's at 0, it will be c0. So let's say I define from c0 to x, and p of x or p of y, d of y. Okay, if I integrate it, you see what will you get? So this will be c0x or c0y plus c1 y square by 2 plus c2 y cube by 3 dot 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 plus cn y n plus 1 upon n plus 1. Right? And this is since this is a definite integral, I'll have the limit, the value will be taken at y equals to 0 and y equals to x. So what I get is, my function is c0x plus c1 x square by 2 plus c2 x cube by 3 plus dot 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 Cn x n plus 1 by n plus 1. Okay, so this is the function what I have got. Now again, this is a continuous function. Clearly this is a continuous function. In fact, it is differentiable. I don't know whether you are aware of fundamental theorem of calculus. Are you aware of that theorem? Okay, even if not, then this from here only you can see this is a polynomial, so it's a differentiable also. Okay, and what you can check is that the derivative, if you do, because how you have obtained f, you have integrated p. Now if you differentiate f, you will get p. That's all. So, and this f prime of x will be nothing but p of x. Okay, so these are the three immediate information what I can obtain for f. Okay, now what we have been given is that this coefficient has this kind of relation. You can see if I put x equal to 1, I am getting is exactly this thing, this one. If I put x equal to 1 in the function f, right? Another thing is that if I put x equal to 0, then also it's becoming 0, right? So you see that f, so note that f at 0 is equal to 0 and f at 1 is also equal to 0. This is given because of the condition that has been given. Okay, so maybe due to given condition. Now since it is 0 at 0 and 1, then by Rolle's theorem again you can say, so by again Rolle's theorem or the mean value theorem, you can say that there exists some point C between 0 and 1 such that f prime at C is equal to 0, right? And this is what you were required to prove, because f prime C is nothing but p. This implies p at C is equal to 0. So you have got that there exists at least one root where the function or one root of the polynomial p. Okay, so in this way you can solve this problem. Okay, is this okay? Okay, now let's move to the next problem. We have to find all the functions which satisfy this kind of, if it satisfy this kind of relation. My claim would be that from here you can conclude that the function is constant. Okay, so I'll just write the claim. So the claim is that f is constant. Okay, and how you can prove is, the proof is very easy, only the guess is hard. The proof, now once I tell you that it's constant, the proof becomes very easy, because you can see, so you can see from here what I can write is mod of fx minus fy, okay, upon x minus y is less than equal to x minus y, right? Now from here what, so suppose if I fixed y, I mean if y is fixed, okay, or maybe you can write it in this way, maybe that would be a better way to write. So suppose if I choose x to be x plus s and y is just x, okay, and this is f of x upon h is less than mod h, right? It's exactly, so here I have chosen y to be x and x is just translation by h, because this is the way we define the derivative. So here also you would be comfortable if I remove y by c, then I think you will be more comfortable, right? Okay, so now if you see, this is nothing but the derivative of, I mean if I take right here limit x going to c, then this is just, if you remove mod, that is the derivative, correct? Yeah, so what you can say from here is, okay, maybe I can just go with 1. So what I can do is, let me remove this one, I think this is fine. Okay, so what you can see here is, now you can bound this also by 0, right? And you know that this limit goes to 0, so limit x going to c, So this would imply that limit x going to c mod of fx minus fc upon x minus c is equal to 0. This is by sandwich theorem or a squeeze theorem, right? And this tells you that the mod of f prime at c is equal to 0, and this is nothing but f prime at c is equal to 0. But c was arbitrary, right? So maybe here initially I should write some line to make sense of this. So let c belong to R. Be any number, be any arbitrarily chosen number. Okay. Okay, then it says that f prime c is 0. That means that is f prime is identically equal to 0 on whole R, correct? And this tells you that f is constant. Okay, so the function which satisfies this kind of identity or inequality, it has to be a constant function. Yeah.
Sir, if the result hold, if instead of 2 we have alpha such that alpha greater than or equal to 2.
Okay, this result you are saying. Yeah, correct.
Yes,
what
sir.
you are saying is not greater than equal to 2. In fact, greater than 1 is enough. Okay, I got your point. So what you can say is, so you look at this relation maybe. So here if you want to replace this 2 by alpha, then alpha greater than 1 is sufficient. Okay, the reason being you don't need greater than equal to 2, just greater than 1 is sufficient, because here you see I can write here 1 minus alpha, right? I mean 1 minus alpha not, but what should I write? So alpha 1 I am taking outside, 1 I am dividing, alpha minus 1, sorry, correct? I can write this relation will still hold true, because this limit is again going to be 0, because alpha minus 1 is positive. So this quantity is greater than 0, right? So this limit is still 0, so again you will get the same answer, that the limit will be 0, and then this everything will follow up. So over here you can replace this 2 by alpha, where alpha is strictly greater than 1. Okay, so now let's come to this problem. So over here you have been given that f is continuous on AB, differentiable on open interval AB, and you have this fa plus fa is equal to fb is equal to 0. So now you have to prove that there exists a constant c such that this alpha fc plus f prime c is equal to 0. How do you solve this one? Any guesses? Okay, before going to solve this problem, can you tell me how do you solve this kind of OD, y prime plus alpha y equal to 0? This is a linear OD, right? Linear first order OD. So you kind of use this integrating factor thing. You multiply by integrating factor, and in here like it will be just, so suppose this is y prime t and yt. So you multiply by alpha t. Okay, then what you have is y prime t exponential alpha t plus alpha yt times exponential alpha t equal to 0. Now you see that this is nothing but yt exponential alpha t derivative prime, this is equal to 0, right? And then you say that this yt is nothing, so because this is constant, e alpha t is constant, so you'll get yt is c times exponential alpha t. This is what how you solve this ODE. Now this is nothing but this same kind of thing is there. This f prime c is nothing but y prime of something, right? So over here you have to basically, the question is not exactly the same, but this will help you to find the function g, okay, where you can use the Rolle's theorem or some mean value theorem. Because you see here it's just saying that from here what if you apply the Rolle's theorem, you will get f prime c is equal to 0 for some c. But the question is not asking about f prime c is equal to 0, it's asking about this kind of problem. Okay, so here being motivated by this kind of ODE theory, what we can say is we'll consider g. So consider function, so consider the function g of x equal to e of alpha x and then the same this thing, so f of x. Okay, so now maybe I can rub this off. So we consider this function. Okay, now you see g at 0 is going to be 0 because f at 0 is 0. Sorry, here it's a and b. So g at a is 0 and g at b is again 0 because f at a and f at b is 0. Correct? So we have got this thing. Then this implies by Rolle's theorem, there exists c belonging to a comma b such that g prime at c is equal to 0. Now you just differentiate this, you will get e alpha c f prime c plus alpha e alpha c f c equal to 0, and this means that f prime c plus alpha f c exponential alpha c is 0, and this will give you that f prime c f of c is equal to 0. Okay, so this proves this result. Okay, so whenever you see problems of this sort, whether you have been given continuous on closed interval, differentiable on open interval, in such problem try to go with some mean value theorem. Okay, so that's all for today. So do you have any question to ask? Do you have any doubts?
No, sir.
Okay, so if there is nothing to ask, we can stop here. Okay, then bye.